Nice to have so much time. I got mine now. Unfortunately, I have no so scientific method presentation. It's just one industrial work, so we have some problems in the practice. And you will see how we solve one very concrete problem from the industry with my PhD student who is the technical director of that company. So unfortunately, he's not here. His name is Ivan Milosavljević. The other one is his brother, Janko Moro. They both are my PhD students. And the last one is Professor Gubeljak. He is also here from Maribor, so he is the co-author of that paper.
Could you please stand closer to the laptop?
Oh, okay. There is no interaction with the auditorium. In that case, okay, no problem. Okay. Okay, I will give you some outlines what we did practically in our work, some calculation of the dynamic force. You will see what that means because it is one mining of the limestone in Croatia. And there is a problem. I will give you the picture so maybe you will understand better. With one diverter pipe, which is heating by the stones, and we should practically estimate the temperature, and after that also the fatigue and fracture. So we made fatigue strength analysis and fatigue fracture analysis, and at the end we put our data to synthetic failure assessment diagram integrity assessment procedure to find the final crack value which would be critical for the pipe. Okay, this is one query with the name Gir Kalon near Drniš in Croatia. This is southern part of Croatia, where we practically have some products, calcite lime, hydrated lime, and stone aggregates. So what it means, maybe in next slides, we will understand better. This is just chemical data, how the limestone practically has been produced by a calcination temperature of about 1,100 kelvins, and how we produced at the end practically the thick lime, slaked lime, and at the end we are practically ready for the market. Just few slides that maybe have better feeling how looks the lime production plant of this company. It consists of some following technological parts. Very important one is rim shaft kiln. On this figure, you can see here the transport line for filling and emptying of the kiln with the stones to be prepared practically for it is limestones to have at the end the lime. So what is the problem? The problem is with that pipes, it is practically not so good because I have to go to show something. This is some kind of the pipe diverter, and we have some problems with that because if you have different sizes of the stone, you should differentiate them somehow. And the problem is how to regulate them. And I really didn't make anything, but okay, this is the story as again in Belgrade. Nothing new.
There's no snow in winter.
Okay.
Was angry because you left.
Okay, I will do it. No problem. I understand. Okay. How it looks maybe in more details. This is the transport line with the stones and some guys who are working there. And as you can see, a very different size of the stones. And after that transport line, the stone is coming to some deep diverter pipes, which are differentiating the stones by size. I really don't know what is going on now. I didn't tell anything. No. Okay. But I have to make something to show you something. I don't know, it is not good. So, for example, this is the divided pipe. And the problem is that pipe, because the stones are hitting that pipe. And the first problem was how to calculate the damage from this hitting, from the 2 meters of the falling down. And after that, what kind of damage, and after also some cracks will be happening there. And we will try to find practically at the end what the crack size will be critical on. Okay, here are the channels and some certain number of pipes inside and pipe diverters also. So depending on the number of inserted pipes, it is possible to regulate which chamber in the cell is going to be filled and how much. And there are 4 thick wallet pipes. The dimensions are 950 millimeters in length of all of them. And outer diameter was almost 90 millimeters with the wall thickness of 12.5 millimeters. It means that it's thick walled pipe. And okay, I don't know what is going on.
Okay, so you'll not touch anything.
Okay. Okay. For the first, we will try to find the deflection of the pipe after the falling down of the stone from the 2 meters by 45 angle. And just some details. Limestone is about density of 2,705 kilograms per cubic meter. Stones are with a diameter of 150 to 250 millimeters as the most worst scenario, but in reality, it's practically from 60 millimeters inside to maybe 150 fraction. Mass of the biggest stone was about 22 kilograms. So maybe you can imagine that 22 kilograms practically is falling down freely from 2 meters of height. So dynamic deflection is not the same as that one. We will see later on. And this load practically we should find to know what kind of damage we can expect after that. Okay. How it looks, it is just some simulation. I hope it works. Yes. What is going on there when the stone is going from 2 meters, what kind of damage we can find there. And after that, okay, we try to calculate something because there is relatively known expression for the static deflection. You can find it here relatively easy by this formula from the literature. And there is also some correlation between dynamic deflection and static deflection. So to be able to find the force. So please have in mind that this force practically is much more bigger than static one because it is dynamical one and it is about 13 tons. Right? Just on the 22 kilograms of the stone, we are coming now to 13 tons of the stone because it's the dynamic problem. Okay, some also detail about the material. We try to solve the problem, of course, by finite element analysis. So just for the one pipe, and where is the stone hitting the pipe? This is the boundary condition for the displacements. It's equal to 0, and it is fixed there. And at the end, we used some different theories to calculate the dynamic strength. In this paper, it was one combination of Goodman, Gerber, and Soderberg models. So very known from the fatigue theory. And here we used Goodman's dynamic strength criterion, which is considered as more conservative compared to the Gerber's one or Soderberg criteria. So just few results. For example, this is equivalent stress according to the 1 meter strength criteria. And we can see that the maximum equivalent stress is below the yield strength of the material because it was 346 megapascals and here is about 262 megapascals. So we are below the yield strength of the material, but still we have the there. We found also the number of cycles until fatigue failure occurs and also what amount is of the material damage there. Also you can find some results on the figure. And we did also fatigue sensitivity diagram and we concluded that during operation about 100 tons of stones pass through the channel in 1 hour. It means that practically 1.2 stones per second fall on the pipe. So this is relatively big frequency of the hitting of the pipe. And according to these results, the fracture will occur after 35,000 of cycles, but means practically 7 hours and 46 minutes of work. This is one shift. It is relatively very small amount of time. It means that something is really problematic. And in the reality, unfortunately, it's not so catastrophic. Maybe 1-5-day change, I don't know, every maybe 2 or 3 weeks, not after one shift of the time working. So it means that something is different, but the difference is based on that we practically use the most worst scenario, because we just use the biggest stone which is falling down, not all the sizes of the fractions and the other things. But in practice, to be sure, the material of diverter 5, it was practically very good construction steel, has been replaced after some time with Hardux 450 at the end. Okay. So we also did the fatigue fracture analysis, because we suppose that what will be happening if we have some semi-elliptical crack with major radius of 1 millimeter and a minor radius of 0.5 millimeters, which has been initiated at the place where the stone is hitting the pipe. And we made 6 contours of 0.04 millimeters element size. They are defined around the tip of the crack. We try to find stress intensity factors for 1, 2, and 3 mode type of the fracture. So here are the results. The third crack growth phase was not considered in this case. Paris contact C and M were practically obtained from the literature, and the dominant type for sure of crack opening is defined by the K1 stress intensity factor, because the crack is loaded with tension and type 1. It means splitting or cleavage fracture is dominant. So there are some results for the K1 stress intensity factor for the fourth crack, for example, contour, and it's obvious that it's much bigger than, for example, for K2 or for K3. So it means that the K1 is for sure is predominant. Just also some movies, how it looks. This is the crack propagation. It looks practically until the end of the thickness of the pipe. This is the second phase of the Paris law, which is solved in Hans software. Okay. And we also, in separate analysis, we also calculate the J integral to be sure for the correlation between K1 and J integral. And at the end, we made also the syntax, means failure assessment diagram assessment, to be sure what is that size of the semi-elliptical crack practically still in the safe region of the failure assessment diagram, or it is out of the diagram. So we practically know yield strength and ultimate strength of the material. It means construction steel as 355. This is not a problem. We found also from the literature that K1C or K material is about 35 megapascal square root meter. And at the end, for 1B analysis, option of the procedure, we found that our working point with the semi-elliptical crack size is still in the safe region. So it's somewhere here. It is relatively close to the material of failure assessment diagram. Maybe it is not so far from that line. It means that maybe a little bit bigger crack could be practically critical for such an approach, but still this initial crack is still in the safe region. So at the end, just a few conclusions. I hope I'm on time. Yes, that we found that if you have the most worst scenario, it means that the pipe diverter will be practically broken very, very soon. It means until 8 hours. Fortunately, in the practice, these are a little bit more. So this is the reason we replaced the S355 with one Hardux 450 material. Is much better. And also the crack will propagate by the 50 millimeters from the initial size during the crack propagation phase, and after that will be unstable. So at the end, I can say that we use practically the hardux material as the better one for this pipe, and now everything is much better than before. If you would like to have maybe some question, there are some data of the authors. This is magnolia tree. It is in front of my faculty, and what is interesting, it is of course in blooming there. But what is the problem? It is the climate change because it is always somehow in April or even in May when we have so nice flowers in the front of the building. But now it is already maybe in March or even in start of April. But what is the problem? The students have to pass, mechanics one is the relatively difficult exam in the first semester. If they didn't pass the exam after magnolia practically has bloom, it could be a problem and they probably fail the year. So it's a problem. So just few slides. What we are doing, if you maybe would like to cooperate with us, we are doing, I think, many other things, not just fatigue and fracture, but also, for example, 3D printing recently. So we have very nice results about the topology optimization of the 3D printed structures and the other things. So if you maybe find it interesting, we can cooperate maybe more. I invite you also to publish the paper in our journal. It is Technical Gazette. It is impacted in Web of Science, about 200 papers per year, if you are interested in. And also, I invite you to our city. It's maybe not so big city as Belgrade. It's only 50,000 of the citizens. It's not so big. But it's the 8th largest city in Croatia. And this is just the fortress, which is very close to the river Sava. And over the river Sava is Bosnia and Herzegovina. So we are the biggest city within the European Union. So on the border of the European Union. And of course, you are invited to visit Croatia. So national parks, we have 7 of them, so you are more than welcome. So Croatia is a beautiful country. If you want to come, you are invited. And for the end, it is important to be connected. I think this is the last one, last slide. It is a new bridge, which is built up by a Chinese company, 2.4 kilometers. Why it is important? Because it finally connects 2 parts of Croatia. If not, before, you should go through Bosnia and Herzegovina. It was not so easy because of boomerang shape of Croatia. It's practically somehow separated in 2 parts. So, but now it is practically connected by this bridge. Finally, after 2 years, many people use this bridge, and it is a very nice bridge. But I am worried because such a bridge, maybe 30 or 40 years ago, Croatia was able to make by itself. But now we should invite China to make it for us, so we are worried a little bit for our technical culture. So for the end, this is my last message. Okay, thank you very much.